Okay, so now we're going to continue our H10K kinematics review on the next page, starting with question number 5. So, a particle moves with a velocity in meters per second at time t seconds, and it's given in this function. Okay, so um, find the expression for the acceleration of the particle. So if I'm trying to find the acceleration, I'm going to need to take the derivative of this. So I've got t and I've got sine t squared. So I'm going to need to do product rule to take the derivative of this. So I'm going to make u equal to t, and I'm going to make v equal to sine t squared. Okay? And okay. So then the derivative of t is going to give me 1, and the derivative of sine t squared is going to give me 2t cosine t squared. Okay, so now I can do the product rule. So I'm going to have, I'll replace u with t, v prime with um, v prime with 2t cosine t squared, plus I've got v, which is sine t squared, times 1. Okay, and now I can simplify this. I've got 2t squared cosine t squared plus sine t squared. Okay, all right. Part B. Hence or otherwise, find the greatest acceleration between 0 and when t is 0 and 8. So in order to figure that out, I want to look at the graph. So I type in we're trying to find the greatest acceleration. So here is my equation for the acceleration, and the greatest acceleration is when the graph is at the highest place. Okay, so I hit y equals on my calculator, and I typed in my equation, and I changed the window so that I could see it. Okay, and I've already fooled around with the window, so let's just stick with what we've got. Okay, so you will need to fool around with window settings. Probably don't have the right number of curves, but anyways, you get something like this, and then do second trace. We want to find the maximum, left bound, right bound, guess, and then I find the maximum point. Okay, part C. Okay, this is a question on using antiderivatives. So we haven't quite gotten to this yet, but you may already remember antiderivatives from last year. So find the expression for the displacement of the particle. So the displacement of the particle is where the location of the particle. So the antiderivative of t sine t squared is going to be negative 1/2 cosine t squared plus c. Okay. Um, so the particle starts at the origin. So that means at time t, the location is 0. If it starts at the origin, the location is going to be 0, and the time is going to be 0. So I place 0 um, in for s, and I plus 0 in for t. And then cosine of 0 is 1. So now I have 0 equals negative 1/2 times 1 plus c, so c has to be 1/2. Okay, and so there is my equation for the displacement. the location of the particle. Okay, hence, show that the particle has never had a negative displacement. This one took me a little bit of thinking, but the unit circle cosine t squared is always going to be less than 1, so we need to remember that. No matter what t squared or whatever is in this parentheses, cosine of whatever is always going to be less than 1. And we also have, we know that we've got a principal axis of 1/2, because that's what c is, and we have an amplitude of negative 1/2, which is what we have here. So since the amplitude is 1/2 and the principal axis is 1/2, the graph is always going to be above the x-axis. Okay? You might need to hit rewind and play that again if you need to hear that one again. Okay, so find the derivative of this. So the first thing I do, so if I see the sign, a little 2 there in theta, this is the same thing as writing y equals sine theta parentheses squared. Okay, so to find the derivative of this, this is easier to just to write the chain rule. Okay, so y equals u squared, u equals sine theta. So dy du is 2u, du d theta is cosine theta. So now I've got 2u times cosine theta, and then I replace u with sine theta. Okay? Next. Hence, find the value of theta in which the derivative equals 2y. Okay, so we know the derivative is this, sine 2 theta cosine theta, so I'm going to replace it with that. And we want this derivative, 2 sine theta cosine theta, we want that to equal 2y. Okay, so we know y is sine 2 theta, so I'm going to replace y with sine 2 theta. And now my only variable is theta. I've just replaced y with sine squared theta. Okay. So, so this is true when sine theta equals 0, because I would have 0 times stuff equals 2 times 0, right? So if sine theta equals 0, then this side will equal this side. So, because, like, as I just said, 2 times 0 cosine theta equals 2 times 0. Okay. So what is going to make sine theta equal to 0? So if I got out my unit circle, what makes sine theta equal to 0? Sine theta equals to 0 at 0 degree, 0 radian, and at pi radian. Okay, so this point and there, and so that's our theta has to be 0 or pi in order to make sine theta equal to 0. The other place that it's going to be true when cosine theta equals sine theta, because if I've got cosine theta equal to sine theta, then 2 times sine theta equals 2 sine theta squared. So when is cosine theta equal to sine theta? Right here. These values are the same at pi over 4. Okay, next page. Okay, so we've got this picture here. So if you want to see this picture, you can type it in to your calculator. Be careful, I made a mistake where I had forgotten to write this x, and it really didn't look like the graph. So let's just do this. So 7 cosine x minus 5x to the power of cosine Okay, and what window I'm going to need here. So window 0, 7, oops, minimum of -30, maximum 10. How does this look? Okay, so this looks just like this graph here, right? See, the same. Okay, so I just wanted an example here. Notice I scratched all this stuff out. And if you do that on the IB test, they can't, even if you did it correctly, if you've put a line through it, they cannot, the person grading the test cannot give you credit for it because you've crossed it out. So if you cross something out and then you realize, oh, that was correct, you have to rewrite it. So that's exactly what I did here. So what does the first question say? Find the initial velocity of p. So the initial velocity of p, of this particle p, is when time equals 0. So I've got this equation, and I can replace cos t with 0. So I have 7 times cosine 0 minus 5 times 0 to the power of cosine t. So 5 times 0 to any power is going to give me 0. Cosine of 0 is 1. So I have 7 times 1 minus 0, and that's going to give me 7 meters per second. I do not know why I crossed that out, but this is right. The answer key on this thing here said that the answer was 17, which is not correct. So, okay. Find the maximum speed of p. So the maximum speed occurs when the absolute value of v is greatest. So here we can see the absolute value, the greatest velocity is when, because this is my function for velocity, right? So this greatest velocity is going to be when this distance is greatest. So I've got this already in my calculator. I'm going to hit second trace. I'm going to go 3 to the minimum because I want to find this location, which is the minimum. And then left bound, right bound. You know the process, right? Okay. Enter. Enter. I guess I hit enter. And this location is 6.37. Okay. So there's my maximum speed. Okay. Question C. Write down the number of times the acceleration is 0. So the acceleration is 0 when the turning point, acceleration is 0 at the turning points of the velocity graph. So the turning point, so at this point here, at this point here, and at this point here, when the velocity changes, then my acceleration is going to be 0 at all 3 of these points. Okay, so there are 3 turning points, so that means 3 times the acceleration is 0. Okay. Find the acceleration p when it changes direction. So it's going to change direction when the velocity is 0. So basically at this point right here, the velocity is positive and then the velocity is negative. So the acceleration of p when it changes direction is going to be this value. So the first thing I need to do, I need to figure out this value for the velocity. So if I use my calculator, I can figure this value out. So I do second trace. I want to find that 0, enter, and then I need to go do the left bound, right bound thing. Do, 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 do. Almost there. Okay, enter, enter, enter. And then you're going to see that x is equal to 0.8638. Okay. Now, we're not done yet. We're trying to find the acceleration of p when it changes direction. So now, to find the acceleration at this value, I need to take the derivative at this value. So I'm going to go, I'm going to do second trace, and I'm going to go down to 6 here because this gives me the derivative of that function that we have typed in there. So, and now I'm going to type in 0.86385, enter, and that gives me the derivative when x is 0.8635, and that derivative is negative 9.24. So this gives me the acceleration when the velocity is that amount. Okay, so you may need to hit reply or reply. You know what I mean. You might need to rewind and see that again. Okay, next. Question 8. At point P moves in a straight line with velocity, and here's the equation of the velocity at time t, where t is greater than 0. Determine the first time that the velocity is 0. Okay, so let's type in this equation. Clear. Okay, so I have e to the power negative x minus 8x squared times e to the power negative 2x. Okay, and my window is going to be this: 0, 10, negative 1, and 1. Okay, let's graph this and see what it looks like. Okay, so it looks something like that, right? Okay, so we're trying to determine the first time that the time hits a 0 velocity. And this is the graph of the velocity. So the first time it hits the 0 velocity is right there. So I'm going to have to do second trace and hit 2 for 0. And then I do the left bound, right bound thing, and then I'm going to get this value. Okay. Find an expression of the acceleration of p. So we've got this equation, right? So the derivative of e to the negative t is going to give me negative e to the t, and the derivative of negative 8t squared e to the negative 2t, I'm going to have to use product rule. Okay, so u is going to equal to negative 8t squared, v is going to equal to e to the negative 2t, and then I take my derivatives and I do product rule. Okay, find the value of the acceleration of p at time t. So the value of the acceleration at time t, I can do second trace, and once again I can hit 6 in this derivative. So I've got my equation in here, and we know t is 0.441, right? So I'm going to hit second trace. I'm going to go down to here because I want to find the acceleration at that time. So I go down to 6, do IDX, and now I'm going to type in 0.441, and this is going to give me the derivative at that point, and the derivative at that point gives me negative 2.276, which rounds up to negative 2.28 meters per second squared. Okay. Okay, next question. Particle P moves in a straight line for 5 seconds. Its acceleration at time t uses this equation. Okay, write down the value of t when a equals 0. Okay, so when a equals 0, so here's my equation, right? I can type it into the calculator, and I can do second trace and find the zeros left bound, right bound. I'm not going to go into that. So the velocity, hence otherwise, find the possible values for t when the velocity of p is decreasing. So the velocity of p is decreasing when we are below the x-axis of the acceleration graph. Okay, when t equals 0, the velocity of p is 3. So find an expression for the velocity. So once again, I need to take the antiderivative of this function. So the antiderivative of the 3t squared is going to be t cubed. The antiderivative of 14t is going to give me 7t squared. The antiderivative of 8 is going to give me 8t. And then we have to put our plus c here. Okay, I'm going to replace t with 0, and I'm going to replace my velocity v with 3. And now I can deduct and figure out that c is equal to 3. And so there is my equation for velocity after using integration, which you may remember how to do. Okay. Oh my gosh, we're almost done. Let's finish this. Have we really gone that fast? I guess so. Okay. All right. We've got to do quotient rule here, right? So I'm going to say u is equal to 2 natural log x plus 1. V is going to be equal to x minus 3. Okay. So the derivative of 2 natural log x plus 1 is equal to 2 over x. The derivative of x minus 3 is going to be equal to 1. So I use my quotient rule, and then I get this. Okay. Hence or otherwise, find the coordinates of the point of inflection of the graph of f of x. So the point of inflection happens when the second derivative is equal to 0. So it also happens when we have a turning point of the first derivative. So at the minimum or maximum of this, right? I should add or when the second derivative equals 0. So I could have gone through the process of finding the second derivative of that, but that sounds like a real pain in the butt. So instead, I thought it would be easier to figure out the minimum or maximum of this graph. And so I typed this equation into my calculator, and I'm not going to do that right now because that took forever. So I can type this equation into my calculator, and I got a graph that looked like this. Okay, and we're trying to figure out the turning point, so like the minimum or the maximum, and so I do the left bound, right bound, and I get this. Okay, and Then, once I get this x value, we're not done yet, I have to plug in the 0.899 into this original equation. And once I plug in the 0.899 into this original equation, I'm going to get the y value. And that gives me the coordinate um, of the point of inflection of this graph. Okay, draw a set of axes showing this. So the first thing I did was I drew the blue graph. I think I need to draw the graph here so you can see what's happening here. Okay. So I'm going to type in the original function. 2, wait, I need opening parentheses. 2 natural log x close parentheses plus 1 close parentheses divided by open parentheses x minus 3 close parentheses, and we need the window to be between -3, 3, -3, 3. Okay, and I get a graph that kind of looks like this. And if I do second graph, I can see, okay, so there's nothing to the left of the y-axis, and I go this way, and it goes down. So notice it says give the equations of any asymptotes. Dun, dun, dun. Giving the equations of any asymptotes. So where do you think the asymptotes might be? Well, when you look at your original equation, notice the denominator is x minus 3. So since this denominator is x minus 3, that means I'm going to have an asymptote at x equals 3. Okay, so the blue graph is my function, which you can see on my calculator. Okay, and we have the asymptote at x equals 3. So how I did it was I did second graph, and then I used some of these points to draw a couple of dots to help me do this. Now, the inverse function is when you switch y with x and x with y. So basically I took this point and I put it here. I took this point and I put it here. I took this point here and I put it over here. And then you can get your inverse function. And you know you've done it right if you draw the line y equals x and it looks like a reflection. I hope that helps, and there we go.